وبركاته. I'm Mohammed Shakir Zahid. Today I'm going to have a short presentation about single degree of freedom of force vibration system. This presentation is submitted to our great instructor, Dr. Fatran Imamudin. As introduction, when a mechanical structured system is said to experience, for example, force vibration system, it has to some energy has to supply to the system during the vibration, actually. Because of this, we call force vibration system. We have harmonic response or transit response. The harmonic response refers to how system reacts to a periodic force. This response could be steady and predictable, actually, but the transit response describes how the system reacts to a sudden, for example, input, or just like a push or a shock. This could be not steady, actually. If the frequency of excitation, for example, matches the frequency of the natural frequency, matches the natural frequency of the system, at the time we have resonance that leads very high response, and the resonance to be avoided actually in mechanical vibration systems because of the failure. Sorry. Equation of motion of a simple system, a simple force vibration systems. What is that actually? We have, as we see in figure 3.1, we have a mass by M and a spring, a damper, a force acting on this mass, actually equal to the mass. How much is it accelerates plus damper damper by the velocity, and spring constant by that displacement. The homogeneous part of this equation, or we can say the steady response or transit response, not steady, the transit response would be the left hand side of the equation 3.1. If we look this equation, the left hand side equate to the 0, and then we have a transit response. But in first, the particular part of the equation of motion represents the steady, the steady. This is steady. This steady response that will be appeared as long as the force in function presence. If there is no force, there will not be steady state response. This means next one, we have response of an undamped system under the harmonic force. If we don't have undamped, for example, the previous was a general. Suppose we have a systems, just like previous slides as I showed you the figure, but we don't have a damper. The equation of motion will reduce to this with the late and the damper term. The transit response of this equation will be given like this, the transit response, actually. And because of this is derived in bulk, you can derive from here, and also taking taking x, for example, the derivative of the x in terms of the Laplace s, and finally, or you can find the root for this equation 3.3, that is s1 s2. Once you find the root of this equation, you will easily get this term, the equation 3.4. Because of the excitation force, Ft is harmonic, the steady state response also should be harmonic. Because of this, we have a generic form for steady state response like this. X is amplitude, actually, By substituting equation 3.5 to the equation 3.3, we will get x as a value of like this. The derivative could be easy actually. Take the value, the derivative of xp in particular, first derivative, second derivative, put in the equation 3.3, then you will get the value as equation 3.6. The types of response based on the ratio, actually a ratio of the frequency of the force frequency to the natural frequency. If we look at if this ratio is between 0 and 1, the steady state response will be same as the force response. And that's harmonic. If it is greater than 1, then the steady state response will be negative actually. If you look at here, it starts from negative. And if it is greater than 1, then there will be resonance. Actually, the amplitude gradually increases. The amplitude increases. Look at the figure 3.6. The response of a damped system under harmonic force. We discussed shortly the response of undamped system, but if we have a damped system, what will be the response? Just we add, as first slide, we add this part to the equation of motion, and we will get the transit, the particular solution as transit as steady state response, just like this equation, like this equation. And the transit response is shown as discussed in chapter 2, but we can find here. How we get this term? If you find the root for equation 3.24, then you will get this value. X as the amplitude, because we have this term. We just zeta and omega n t, or we can write this term as omega d, as it's shown for underdamped system. We have a general solution here. We just add the particular solution to the homogeneous solution, or the steady state response to the transit response. We will get the general solution as just like this. Here we wrote omega d. Omega d is equal actually the square root of 1 minus zeta square by natural frequency. If you look at this figure, easily we will understand lots of properties on amplitude ratio. Amplitude ratio versus frequency ratio, and phase angle ratio versus frequency ratio. We have two figures. The first figure, if you look at the first figure, amplitude ratio, that is x by the delta static displacement. Actually, if we have the frequency ratio, for example, as one, the amplitude ratio will be infinity. It means resonance. Or in another word, if damping ratio is approach to zero, approach to zero, the amplitude ratio will go infinity. Or the amplitude ratio is united when we have the frequency ratio as 1 and the damping ratio as half, as a value of half. This one here, this point, we have unity of amplitude ratio. The phase angle like this, if you between, for example, the angle between 0 to 90, you almost have a damping ratio range of between 0 to 5. Actually, when we have the damping ratio as 0, it will be the resonance and the frequency ratio. Resonance actually when frequency ratio is equal to the natural frequency, as we stated earlier. Because of this, if we have 1, we have 0 damping ratio here, and phase angle with infinity actually. By the way, the next part also shows the response of system under the harmonic motion of the base. In previous slides, we didn't have harmonic motion for the base, but here the base has a harmonic motion by this equation: yt equal y sine omega t. If we have the base that has a motion, harmonic motion, we add the displacement. This time the displacement, we consider the displacement of the base and the velocity of the base also to our equation of motion here. M as a function, mass actually as a coefficient of the acceleration, and the damper constant as a coefficient of the velocity of a spring subtracted from velocity subtracted by velocity of base, and K spring constant by the displacement of the spring and minus displacement of the base equal to 0. When we don't have a force, it will be equal to 0, but in case also we have a force, but it will not be 0, we have a force. Substituting yt, the value yt, we have the value of yt, for example. Take y terms on right side, we will have this equation, and then put the value of y here, take derivatives of y, first derivative put here, and you will have like this equation, and finally we will have this term, that is A is amplitude, absolute amplitude of the system. A is equal what? Y, capital Y, square root of k square plus damper c omega complete square. C is actually force the system actually the system frequency. Alpha, not the general frequency, alpha, and the angle is equal inverse tan of the minus c omega over k. Response of a system under the harmonic motion of the base. We have already explained shortly, but the generic steady state of response also will be shown by this equation. But it's just generic, it's general. If we go deeper, we will have this. But at the time, the y as a value as a complex, shown as expressed as a complex number, for example, the function of a complex number like this, we will have the particle solution or the steady state response by this value xp equal or e like this. And the displacement translationality, is actually the ratio of the x by the capital Y. That is shown by TD equal this value. Later on, we will see some effect. Displacement translationality, this ratio to the verse frequency ratio. We will see that if we have a frequency ratio of square root of 2, our displacement translationality actually united, but this one united. But when we have a higher square frequency ratio higher than square root of 2, the displacement translationality will decrease till infinity. And how much how much the damping ratio here decrease or approach to zero. Again, the displacement of transversality approaches to infinity. This is short demonstration. We can design different base different systems that has base harmonic motion by this relation. Simply, if you understand very well, the frequency ratio versus angle phase we have also here. Chart. For example, if we have frequency ratio 1 and for example a phase angle for the damping ratio as half, we will have almost phase angle as 45 as before. When the damping ratio is zero and the frequency ratio is equal 1, it will be the resonance. The phase angle will be between 0 to 180, 0 or 180 like this. Force transmissibility. We covered displacement transmissibility, but here we have force transmissibility. In figure in 2 slides before, in figure 3.14, if force if transmitted to a base or supported due to the reactions from the spring, this force can be determined as I told you. If at that time we didn't have the base system, we didn't have a force, but here we have a force. If we have a force acting on it, we find the force by this relation. Just equate this. Equate the damper constant and also spring constant by the displacement, by the total displacement equal to the mass by acceleration. That is force actually. The ratio Ft over ky. Ky, we have the value, we find the value of y. Put the value of y. What we have in value of k. Then we have this ratio. This ratio is called force transmissibility. That if we plot a graph or a diagram, for example, from frequency ratio to the force transmissibility, we will have like this graph. It is almost the same idea as before, but with different of course value. In this side we have rotating unbalance. We have rotating unbalance. How much it is when it's unbalanced. Response of a damped system under rotating unbalance. Here in the system, the rotating unbalance actually, what is the cause? The cause is when two masses are actually not equally distributed, the unbalance will occur. The initial response will begin actually when the system experiences sudden vibrations due to the unbalanced force, and the steady state response actually when comes or when we reach the steady state, that we minimize the vibration, indicating the instability actually. The application of this, the practical application of this, for example, systems under rotating unbalances to minimize wear, failure, noise. If we analyze this system, for example, as shown in this figure, this variable diagram, this two mass, this mass, M capital is expressing total mass. If we analyze this, we can reduce or minimize the wear, failure, and the noise. Then almost the noise also actually occurs or produced because of this unbalance. Self-excitation and stability analysis. When excitation of force, when excitation force in the systems is a function of what motion parameter is a function, for example, velocity or displacement or acceleration, this system actually is called self-excitation vibration. Because of this, it's not external force, it's internal force. Dynamic stability analysis is when a system, we can say a system is stable or motion that the motion remains constant, or the displacement remains constant with the time, or steady with the time, not constant or steady with the time. Vice versa, if the amplitude of the displacement increases the displacement with the time, it is to be dynamically unstable, actually. Dynamically stable, or in another word, if C and K are positive values, assuming that M, that's mass positive, we will have dynamically stable system. This is just a representation equation of motion after a derivative of derivation of the equation of motion. S squared in terms of the Laplace transfer signs, or in terms of the S signs. This shows acceleration, this shows velocity. There we have displacement divided by the unit of mass. Second one, we have in self-excitation and stability analysis, dynamic instability caused by fluid flow. When fluid, for example, suppose a cable of electric networks that's connected for transferring electric energy. When wind actually pushes this cable, it creates vortex around the wave, around the cable, for example. When the force, when the air comes like this, it creates at this side a vortex. This vortex causes noise that we can hear during a very fast wind. How we can, and also it causes the vibration for the cable. Actually, in the time it could lead to the failure of the cable. How we can reduce this vibration? Just by designing a damper vibration absorber known as the stock bridge damper, that has two masses and two ends. One is this end, this end. We place it where the cable experiences a large vibration. Transfer function approach actually is a good approach to solve or to get the response of a force vibration systems. The transfer function actually converts the differential equation into the polynomial equation and algebraic equation that leads to very easy solutions. If the transfer function is known, the output of the response also can be found easily. For example, it deals with the input. It is a block diagram representing of input systems and output systems. We have input system as fx, systems at ts, transfer function output system as displacement here. If we suppose this equation, how we convert to the transfer function? Simply take Laplace of the all terms of the x. This will, but considering initial condition as 0, we will have s square s and here 1. The common factor is x. Take this term, and this side will be fx. Take fx this side, fx this side, and take this term to this side. This will be 1, this will be this term. We will have this equation, that is ds output is xs for input fx equal this. This is the response, isn't it? Solution using the Laplace transfer function. Here, response of a damped system. Show the damped system Laplace transfer function. This damped system. Look, we can easily, as previous, we can easily get this solution. How we can find this value? Because 2 zeta omega n is equal s. Am I right? We can put the value of s is c. Sorry, c. That is damper constant. And also we had here k over m. Actually, it is omega n square. We can find this general equation, or it's a special equation. Actually, this term. Steady state response using the transfer function actually found by this. If t equal this value, our response will be added by this value, not added but multiplied by this value. This multiplication, not addition. By undetermined coefficient, we can find, or we can take inverse Laplace transfer of this term. Will be take a little bit time, and we can find easily the solution. This was a short introduction, short presentation about forced vibration system of a single degree of freedom. Thank you very much. So